Thank you. So I don't know how many people I have in the audience, but I think I assume they want to conceptual talk. So it's to that I wanted to listen to him. But anyway, I'm going to talk about the chiral algebras of 0, 2 sigma models, and what are they? Well, they generalize quantum homology ring, and they are related to chiral differential operators, chiral Durham complex, 0 to mirror symmetry, geometric Langlands program, and so on. So they are clearly interesting objects to study. And I will discuss the following 3 points. Number 1, I will say that the chiral algebras can sometimes vanish. It can be identically 0. And I will also talk about the implications of the chiral algebra, vanishing of the chiral algebra for the geometry of loop spaces, and especially the Hensch-Stolz conjecture on the vanishing of the Witten genus in the Kähler case. So what I'm going to say is not going to be rigorous because I will do physics, but hopefully I can get mathematicians interested in this subject. All right, so what is the Hensch-Stolz conjecture? Well, let M be a closed string manifold where string means its spin and 1/2 of the first Mondragon class is 0. And suppose that the Ricci curvature of M is everywhere positive definite. And the conjecture says that in that case, the Witten genus is 0. Well, what is the Witten genus? Well, it's the I wrote down the formula here. So it's a Q series with the coefficients being the index of the Dirac operator twisted by a certain series of vector bundles over M. So for example, when V0 is just a trivial bundle, V1 is a tangent bundle, and so on. So the conjecture has been checked for a number of examples, including complete intersections of hypersurfaces or homogeneous spaces. And there are no known counterexamples so far. So, the formula looks a bit complicated. So where does it come from? Well, it comes from two-dimensional quantum field theory. So consider sigma model on torus, which is a quantum field theory describing maps phi from a torus to a manifold M. And it's a bosonic field. We can add fermions to make the theory to have a 0, 1 supersymmetry. Well, what does it mean? It means you have a self-adjoint fermionic field called supercharged Q, whose square is equal to H minus P, where H is the Hamiltonian, P is the momentum, so it's a generator in sigma direction. And for the quantum theory to be consistent, M must be string. Okay? So there's this condition imposed on M. And if you compute the partition function, a certain complex number, then you will find that it is related to the Witten genus. Well, it's proportional to Witten genus in this manner. So this is the physical origin of the Witten genus. And so phi is a map from the torus to M. But if you specify a time t, then it will be a map from a circle to M. All right, so for each time t, phi describes a position of a circle embedding in M. So we can view this system as we can view as phi as describing a motion of a loop in M. Okay, so this is the idea of string theory. So we can view this theory as quantum mechanics on the free loop space, which is the space of loops in M. All right, maps from a circle to M. So this is quantum mechanics. So we can canonically quantize the theory. And we can translate various quantum field theory concepts into loop space language. So fermions satisfy these anti-commutation relations here. And this is actually nothing but the loop space version of the Clifford algebra, where sigma being the continuous index describing the position in the circle direction. And since besides can act on states, so states, physical states, are spinors on Lm, right? And parity of the state, so either it's bosons or fermions, well, the parity corresponds to the chirality of the spinors. And the supercharged Q, if you canonically quantize the theory, well, it turns out to be equal to the Dirac operator on loop space. And therefore, supersymmetric states, which are annihilated by Q, corresponds to harmonic spinors on Lm. And in this, well, you can compute the partition function from this viewpoint, and you will find that it is equal to the S1 equivariant index of the Dirac operator on Lm. So you take the supertrace in the space of harmonic spinors on Lm with the generator of translations P inserted in the trace. All right, so I introduced this loop space viewpoint. So how does it help understand the Hensch-Stolz conjecture? Right. So why did I introduce this loop space viewpoint? Well, because recall the following theorem by the Lichner-Witz. Right. So he says there are no harmonic spinors on a closed spin manifold M if the scalar curvature is positive. All right. Then if there are no harmonic spinors, then the A hat genus vanishes. So there's a clear analogy between this finite dimensional case and the loop space case. Right? M being spin corresponds to Lm being string. Right? Positive scalar curvature corresponds to positive Ricci curvature. And vanishing A hat genus should correspond to the vanishing Witten genus. So this is the idea that this analogy is what motivated Stolz to make his conjecture. So Stolz thought if there's a loop space version of the Lichner-Witz theorem, namely there are no harmonic spinors on Lm, if M has positive Ricci curvature, if we have such a theorem, then this will imply the vanishing of the Witten genus. So this will imply the conjecture. So Stolz's goal is to construct the Dirac operator on Lm somehow and show that this theorem will show this result. All right, so I thought, well, this is all motivated by physics. Maybe physicists can tell something about this conjecture. But I found this problem too difficult. Yes. All right. Mm-hmm. Sorry, I didn't quite understand the how do I?
Yeah. How can I interpret that Hensch itself?
Ricci curvature of M. Of M. Sorry, I didn't indicate that. Right. So. All right. So, because that problem is too difficult, let us restrict our attention to the Kähler case. Recall, if M is scalar, the Dirac operator splits into two parts, which are adjoint to one another. So curly D, and curly D squares to 0. So we can consider D cohomology. It's called the spinor cohomology. Or similarly here, the supercharged Q splits into two, curly Q, and it's adjoint, and Q squared is 0, and it satisfies this equation. So we can consider Q cohomology in the Hilbert space of states. And by the Hodge theory, well, it should be isomorphic to the space of harmonic spinors on the loop space. Then, in the Kähler case, the loop space Lichner-Witz theorem, if we have such a thing, then it should be the following. The cohomology, the Q cohomology of states is 0 if the Ricci curvature is positive or the first chunk class of M is positive. So this is what I want to show, and which I haven't been able to, but I have some idea to tell you. All right, so I've been talking about Q homology of states, but now I want to consider the Q homology of operators, because Q can act on states or operators. So we can also consider Q homology of operators. And this is an interesting object. So Q homology elements vary holomorphically. The reason being this combination H minus P is equal to del Z bar. And it's actually Q exact operator because of the supersymmetry algebra. So whenever you take Q closed operator O, then del Z bar of O turns out to be Q closed, right? So its homology vanishes. And you can take two Q homology classes of operators and multiply using operator product expansions inherited from the underlying theory. So these properties define a chiral algebra, meaning an OPE algebra of holomorphic fields. So whenever we have a 0, 2 supersymmetry algebra satisfying those relations, we can construct a chiral algebra, which I call A. All right, so I introduced this chiral algebra. So let me tell a little bit more about this thing. So if we can compute this chiral algebra using path integrals, and there are non-perturbative worldsheet instanton contributions. But if we ignore instantons, it turns out that the chiral algebra of 0, 2 sigma model is isomorphic to the homology of a sheaf of chiral differential operators. So what is, or CDO for short. So what is this CDO thing? Well, this sheaf is a vertex, well, locally on M, it's a vertex algebra known to physicists as the free beta gamma system. So it's a free conformal field theory defined by this OPE, operator product expansion. And it satisfies certain, it has certain interesting properties. And for example, when the M is the flag manifold of G, then, well, the homology is a G, well, is an affine G module of critical level. And also, it's a vertex algebra, but nevertheless doesn't have an energy momentum tensor. Well, the standard choice of the energy momentum tensor of beta gamma system, well, so you can define locally on them an energy momentum tensor, but they don't glue globally over M. So you don't have a global section. So when the first Chern class of M is non-zero. So it's a vertex algebra without energy momentum tensor when C1 is non-zero. So physically it's a bit unusual. So, and Witten studied this system perturbatively, meaning ignoring instantons, and yeah, that was this. So he found that it's isomorphic to the homology of CDO, but in that paper, he made a remarkable prediction. Well, take the simplest example, M being P1, then he computed the homology and without instantons, but he predicted that once you include instanton corrections, then this homology, which perturbatively is infinite dimensional, as soon as you include instantons, becomes zero. The reason is instantons will make the identity operator equal to zero in the homology. What this means is that the identity operator becomes Q exact by instant corrections. And therefore, the chiral algebra vanishes because 1 is 0. Right? And this was Witten's prediction, was verified by direct instant computation by my friend Tan, who has been here, who was here 15 minutes ago and went to Masahito's talk. and was also verified, sort of verified by mathematically rigorous way by Arakawa and Malikov in their papers in 2009. And more generally, yes, we have the following result. When M, which is a Kähler manifold, with Kähler manifold contains P1 with trivial normal bundle, then you can argue that the Kähler algebra non-perturbatively with worldsheet instants vanish. So example is the Flagg manifold. And so this Flagg manifold example, so for Flagg manifold, the Kähler algebra vanishes non-perturbatively. And this result was also obtained by Frankel, Lozev, and Nekrasov in their in their recent work. So how does this vanishing theorem of Kähler algebras, how is this related to the conjecture, to the Hensch-Stolz conjecture or loop space Lichner-Weiss theorem? Well, it's because the Q cohomology of states is a module over the Kähler algebra. Well, you can take any Q cohomology class of operators and let it act on Q cohomology class of states naturally in this manner. And if the Kähler algebra vanishes, then 1 is equal to 0 in the Q cohomology. So whatever Q cohomology class of states can be written as 1 times that. And 1 is 0, so it's 0. Right? So it means that whatever Q cohomology class is 0, so Q cohomology of states vanishes as well when the Kähler algebra vanishes. So it means the spinor cohomology of Lm is 0. There are no harmonic spinors on Lm. Therefore, the Witten genus vanishes. Right? So the question is the following. Well, so we know that the Kähler algebra vanishes for the Flagg manifold, and Flagg manifold admits a metric with positive Ricci curvature. So the question is, does the Kähler algebra vanish whenever the first-Chern class is positive? And if we can show this kind of result, then this will imply the Kähler version of the loop space Lichner-Weiss. Okay? So there's some argument I can offer, which is extremely heuristic, so which uses renormalization group law, and that's something like the Ricci law. So the idea is the following. We rescale the space-time, two-dimensional space-time. And under this rescaling, the Kähler algebra is known to be invariant. And first we can squeeze the space. We can make the space very small, space-time very small. And it's known that the quantum effects becomes very small in this limit. It's called the asymptotic freedom if the first-Chern class is positive. So in this case, we can trust the perturbative approximation. We can approximately calculate the Q cohomology. All right. And if we can show that the Kähler algebra in this limit admits no energy momentum tensor, well, this is the crucial part, then we can now inflate the space-time, make it very big. Then it is expected that the theory floats to a superconformal field theory. In that case, the standard, the energy momentum tensor in the superconformal field theory algebra should belong to the Kähler algebra. Well, this seems to be a contradiction. Well, the possibility should be that the superconformal field theory, this theory, is actually a trivial theory with no degrees of freedom, and therefore the Kähler algebra is 0. So this may or may not work. And the crucial part is to show that the Kähler algebra or the cohomology of a sheaf of CDO admits no energy momentum tensor when C1 is positive. So this I've been trying to show, but I haven't been able to. All right, so summary. So I told you that the loop space Lichner-Weiss theorem will imply Hensch-Stolz conjecture. If M is scalar, there are no harmonic spinors on Lm if and only if the Q cohomology of states is 0. The Kähler algebra is isomorphic to the cohomology of CDO, ignoring instants, And if the current algebra is, well, the current algebra is 0, in some cases, in the presence of instance, well, A equals 0 implies the Q cohomology of state 0, and this will imply the loop space Liebniz theorem, and hence, therefore, the Hinge-Stotz conjecture. And the question is, does the current algebra vanish when, if the first Chern class is positive? This is I'm trying to show. All right, thank you.
Should I think of like the incident effects as contributing some differential to this state complex? Kind of like the Floer differential?
Yes, yes. So, all right. So Q, all right. The supercharged Q classically can be thought of as the double differential acting on certain twisted by certain holomorphic vector bundle. And if you add quantum Petagogic corrections, then it deforms this double operator. And instant corrections, introduce some deformation, which violates the grading of the differential bonds. More questions?
I just wanted, I'm not sure this is correct, but this is a very physical way of saying what you just said, is that the instantons destroy the perturbing vacuum, right? They destabilize it, which is quite common. And then usually in string theory, if you have background fields, you get a non-vanishing index. It's a very easy way to get a non-vanishing index, and that would stabilize the vacuum. So I don't know.
Well, this is the system I've been considering is very unusual from the viewpoint of string theory. First of all, it doesn't have moving fermions.
Okay.
So it's not even.
It's a half. Well,
yes.
But you could imagine later.
So you can have all sorts of weird things, I think.
Yeah, usually, I mean, if you give me a chiral algebra, I can usually embed it in a zero-2 model of some kind. It's not
Yes,
difficult
but
to do
usually
it.
with.
But I think what I just wanted to say that I think what we've shown is that it's just that the instanton destroy the vacuum, they destabilize it.
Yes.
And one way of stabilizing it often works in string theory is that you have some background fields and you get a non-vanishing index. So that's just a comment.
Yeah.
It's probably related, right? So you said about this kind of Carol-Durand operator, so it was a beta gamma system locally?
Yes.
There isn't anything analogous with this BC beta gamma.
All right, BC beta gamma system corresponds to the Carol-Durand complex, right. And in this language, in the quantum field theory language, it's more or less what's called the A model. But in the A model, so you can construct the Carol algebra for the A model. It's infinite dimensional, and it's graded by the conformal weight. If you just look at the weight zero subspace, that's the quantum cohomology ring. And then, yes, but if you look at all the higher weight space, you get a certain vertex algebra, and that vertex algebra without instance reduces to the cohomology of the Carol-Durand complex.
Yeah. So what do instantons expect? So are instantons again expected to kill off this algebra or just modify it?
For the Carol-Durand complex, yes. Well, that will never happen.
So it won't kill off.
No.
But I think isn't it the Young mistake that will make the algebra semi-simple?
Or
for the chiral, the anti-institute theory, the algebra becomes semi-simple if C1 is positive. This is kind of supposed to be the analog of what you said.
Well, it's not the non-potability answer is no for the dimension zero, weight zero space. That's the quantum cohomology. But for the whole but the vertex algebra structure is not no.